Section 5.1 is an introduction to normal distributions in general and the standard normal distribution, which is the one that we'll work with most after this chapter's over. So a normal distribution is a continuous probability distribution. So remember in chapter 4, we dealt with discrete probability. Now we are working with continuous probability. So instead of finding the probability of 5 or 4 or 3, now we can figure out probabilities for a continuous number of values. So normal distributions are a continuous probability distribution for a random variable x. When you graph the normal distributions, the graph is called a normal curve. So it will not look like the histogram that we had with discrete probability. It's going to be a curve, and we've actually already seen it. You know, it looked like that bell curve. So some features of normal distributions in general. The first feature is that the mean is equal to the median and the mode. A normal curve is bell-shaped and symmetric about the mean. The total area under the curve is 1, just like it was with our discrete probability distributions. A normal curve approaches but does not touch the x-axis. As it gets further away from the mean. So that is kind of like a horizontal asymptote that we've seen in other classes. There are inflection points. An inflection point is where a curve changes from either concave up or to concave down or vice versa. So it goes from looking like an upside down parabola to a right side up parabola. So there are inflection points at the mean plus 1 standard deviation and the mean minus 1 standard deviation, so that the graph is concave down between those 2 points, between mu plus sigma and mu minus sigma. And then the graph is concave up to the left of mu minus sigma and to the right of mu plus sigma. So what the graph looks like, a normal distribution. It's going to be tallest at mu, and then we'll have space for mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and then mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. So that would be, the mean is going to be the highest point, and then 1 standard deviation above and below, 2 standard deviations above and below, 3 standard deviations above and below. So we've got those inflection points at one above and one below. So what's going to happen is our graph is going to be the tallest at the mean. That will be the tallest point, and it'll be symmetric across that value. And then at mu plus sigma, we have an inflection point. At mu minus sigma, we have an inflection point, so that our graph is concave down in between those points, meaning it looks like a parabola that opens down in between these points. And then it turns around and starts to look like a parabola that opens up outside of those points. But then it never touches that axis. So our graph looks like that. And actually, there's a formula for this graph. There's an equation for it. I don't expect you to know this. I just never knew it before, and I think it's interesting. So if you don't think it's interesting, that's fine. I'm okay with it. Just don't write it down. But the equation for it is 1 over sigma times the square root of 2 pi times e to the negative x minus mu squared divided by 2 sigma squared. So you can actually graph this if you know the mean and the standard deviation using that on your graphing calculator, or you can graph y equals normal PDF and then x mu sigma would give you that graph. Normal distributions can have any mean and any standard deviation. I should qualify that. They can have any mean and any positive standard deviation. The values determine the shape of the curve. Now, what I mean by the shape of the curve is, it's still going to be that bell shape, but where that's located along the number line and how tall and how short it is going to be determined by the mean and the standard deviation. So within these normal distributions, the mean is going to tell you the location of the line of symmetry. And sigma is going to tell you the spread of the data. So what happens there is that if sigma is higher, that's going to give you a graph that is shorter and like fatter, I guess, shorter and wider curve. And the lower sigma is going to give you a taller, thinner curve. The reason for that is that the area under the curve is always has to be 1. So if I'm trying to make a high standard deviation, meaning it's spread out, then if I take my regular curve and I spread it out, then it has to get shorter. If I have a small standard deviation, then I'm squishing my curve in, which means that it has to go up in order to keep a constant area. So let me make a little comparison chart for you here. So this is going to be an example. So I am going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to give you 3 different sets of information. So in my first one, the mean is going to be 3.5 and sigma is going to be 1.5. And I'm going to compare that to a mean of 3.5 and sigma of 0.5. And my third data set is going to be a mean of 5.5 and sigma is 0.5. So the two means that have the two sets that have a mean at 3.5, what that tells me is that my line of symmetry is going to be at 3.5 for both of those. So I'm just going to put my lines of symmetry on there for now. And the mean of 5.5 tells me my line of symmetry will be at 5.5 for that one. So the line of symmetry is the place where the lump is, the highest point. So this is like my line of symmetry. So having a higher mean tells me that my line of symmetry will be more to the right than to the left. So the mean tells me the location for that. The sigma tells me the spread of data. So the higher the sigma, the shorter my curve is going to be because it's more spread out. The lower the sigma, the taller that curve is going to be. So if my sigma is 1.5 on this one, but both of these are 0.5, then this tells me that these two curves are going to have the same shape. They will be taller and thinner than this curve that will be shorter and wider. So remember that my point of inflection is at my mean plus sigma. So on this shorter, wider curve, I'll go ahead and put my top of my curve here. And then if I go 1.5 to the right, that's 1 standard deviation. I'm going to make my point of inflection here and go, oh, I didn't go 1.5. 1.5 would be to here. Go 1.5 to here, and I'll put my point of inflection here. So my curve is going to be concave down in between here, and then switch to concave up and go along the edge. So that's my shorter, narrower curve because my sigma is bigger. Now on my taller, wider curve, this one's going to have to be higher because my standard deviation is only 0.5. So my point of inflection is here at like 4 and here at like 3, which means my curve has to be taller because I have to fit the same amount of area that I'm fitting into this wide curve. So I need to be taller here. So I'm concave down here and then concave up outside of there. These are just estimates. I'm just kind of guesstimating where this would be. And then since this has the same standard deviation, it will be the same shape as my green curve, but it will be moved here up to 5.5. So that means my standard deviations will be, my one standard deviation will be at 5 and 6. So I should have that. My orange curve and my green curve should be the same shape, just like shifted from each other. But my green curve and my blue curve would have the same peak spot. So that's how I can compare based on the mean and the standard deviation. So let's look at some examples and talk about whatever questions they ask. This one right here says, which normal curve has a greater mean? And then which one has a greater standard deviation? So a greater mean means the line of symmetry is further to the right. So which curve has a line of symmetry that's further to the right? That would be A. And then which curve has a greater standard deviation? Greater standard deviation means that the curve is shorter and wider. So my shorter, wider curve would be B. Okay, let's look at this one. Consider the normal curve shown at the right. Which normal curve has the greatest mean? Which normal curve has the greatest standard deviation? So the greatest mean would be the one that's furthest to the right. That's going to be B. And the greatest standard deviation will be the one that is the shortest and thickest, which would be C. Okay, now we're going to have to make some guesses about what the mean is and what the standard deviation is. So here I've got this grade 8 math test is normally distributed, and they want me to tell the mean. Well, the mean is the line where the line of symmetry is. So if I go from the peak point and follow it down and then look at my scale, that's 650 and that's 700, 660, 670, maybe 680. Maybe that wasn't straight down, somewhere between around 680. So the mean is about 680, I would say. And then the standard deviation is where the inflection point happens. So where it switches from concave down to concave up, I'm going to estimate about here. So that's about 710. So then my standard deviation would be from about 680 to 710. So about maybe 30. Now let's look at this one right here, where we have grade 8 English learner language arts test, normally distributed. The normal curve shown below. What is the mean? Okay, mean, remember, goes from the peak. So arrow down to there, maybe like, I don't know, 640, 650, maybe 658. I'm just estimating. And then the inflection point maybe right here.